In this chapter, we'll have a look at some drawings and see what you can do to simplify the life of the machining company and so reduce your costs. This slide shows a part which has been drawn but which has no tolerances. In this case, the machinist will rely upon any default tolerances specified in the drawing title block. It's a good idea to specify default tolerances so that if you forget a particular tolerance, you can improve the chances that the part is still produced to usable tolerances. On the right hand side, you can see some examples of typical default tolerances. A standard tolerance of plus or minus 0.1 mm for distances is used, as this is very easy for CNC machines to achieve, where nowadays decent machines can hit a positional tolerance to within a cube of 15 microns per side. Hence the default position tolerance of within a cylinder of diameter 20 microns. Angles are much tighter, and half a degree is actually a very small tolerance for most parts. Let's now have a look at some CAD drawings. This drawing shows a flattish plate, which has a couple of bosses sticking out of it. The first thing that we typically do is make sure that we tell the machinist how to hold the part. We do this by specifying datums. Normally for datums, I like to use a couple of holes as far apart as possible, plus a flat surface. This means that the part is restrained in translation and rotation in all directions. Choosing holes that are far apart as locators means that any features between them will be well positioned when mounting the part. In this case, however, the holes around the edge of the part are clearance holes for the bolts, so they are not tightly tied up with tolerances. However, the holes in each of the two bosses appear to be more important and are likely to have tighter positional requirements, so we'll choose those as datums. You can see in this version of the drawing that we have chosen the large flat surface as our main datum and then the two holes as our remaining two datums. Looking now at this drawing of a cone, we can see that the fitting diameter is specified along with the distance from the end of the part. The argument here is that whilst the function of the part is dependent on the dimensions given, it's hard to measure something part way along a surface. Instead, it's much easier to measure the end diameters and the part length. These should be given as reference dimensions, which are shown in this version of the drawing. You may choose to set up your inspection once to measure the functional diameter and distance, but the next time a batch of these parts comes in, you can simply measure the end diameters and length, which will make the inspection quicker and cheaper, leading to cost savings on your parts. Another way to save costs for batch parts is to specify what proportion of the parts should be inspected. For large batches you might say 1 in 1,000 parts or 1 per batch, depending on how critical the tolerances are and the historical reliability of the supplier. You can do that with a marker symbol, and you can see in this version of the drawing that the triangle is shown beside the dimension and in the notes as meaning 100% inspection of this critical dimension. We just have time now for a quick ad before we move on. That was fun. Now, let's carry on. With this next example, we'll look at dimension grouping. Looking back at the drawing of the battery module end plate, we can see here a poor example of dimensioning. The dimensions for the critical hole in section EE are partly listed in the cross-section, but other dimensions for the same hole are listed in the view below or in the section BB. This version shows a much better way to dimension the holes. The relevant dimensions are grouped together in the same view as far as possible. This saves the machinist from having to spend time searching for the dimensions, thereby reducing cost to you. This drawing shows the final version. The last point I want to make is shown in this drawing here, which is the top part of a connecting rod assembly. There is a lightning pocket in the side of the part. In this case, we've specified the tool type and dimensions as well as the tool path, which means that the tool path can be programmed offline directly on the machine, rather than by using specialist CAM software, again saving time and cost, whilst achieving the result that you wanted. Without these instructions to the machinist, the pocket could have been made by interpolating a small diameter cutter, taking more time and leaving stress razors at the step over points. This concludes the section on drawings, and you should now have a few tricks up your sleeve to save manufacturing time and cost. Let's move on to the last section of this mini course, Tricks of the Trade.